Are we ready to continue on our great journey into statistics? Kind of, sort of, maybe. All right. So we were in section 2.1, and we're looking at frequency distributions. The last thing that we did was we created a frequency distribution. Yes. The key thing to remember was whenever we say frequency, we mean count or how many. Yes. Well, along with our frequency distribution is something called a relative frequency distribution. And your relative frequency distribution, we're simply converting everything into a percentage, converting everything into a decimal. All right? Another way of saying that is converting it into a proportion. Your relative frequency is found by taking the class frequency and then dividing it by the total frequency, and that gives us our relative frequency. Questions there? So if, for example, on a test, you got, say 18 out of 20, or if I told you got 90%, I'm saying the same thing, correct? Right? The difference is that when you're using the relative frequency, when you're using the proportion, that allows you to compare data. So if you had two quizzes, one quiz was out of 20 and another quiz was out of 10, you can compare both of them. If I say I got 90% on the first and 90% on the second, it means I did exactly the same. I did just as well on each test. Yes? And so that's why we have this inkling or this desire to convert it into a relative frequency. Questions there about relative frequencies themselves? The idea of converting into a percentage instead. Yes? Good afternoon. Actually, let me skip ahead and come back. So, where's my relative frequency table? So this is right here is a classic example right here. Over here, we have a regular frequency table, and then over here you have your relative frequency table. So for example, in this chart right here, scores between 1 and 8, this looks like 13 people scored between 1 and 8, yes? And then between 9 and 16, what's that? 18, 19, 20, about 21 people scored between 9 and 16, yes? If I convert it into a relative frequency, this right here is saying that about 22% of people scored between 1 and 8. Yes? It is now a percentage, but look, the tables look exactly the same because they are. I'm just converting it into a percentage instead. Questions there? So I'm not changing the data, I'm just putting out of 100 instead. Yes?
Explain what a relative frequency is.
A relative frequency is taking the scores and converting them into a percentage. That's all it is. So for example, if this was a test and I scored 18 out of 20 on the test, the relative frequency would be 90%. Just dividing the two, 80 divided by 20. Right? The total on the score was 20%. I scored 18. Questions there? And that's why they're exactly the same. I'm just representing it differently. I can either say you scored 18 on that test, or I can say you got 90%. But I'm saying the same thing, yes? And so that's why the two tables look exactly the same. Questions there? All right, let's go ahead and create ourselves a relative frequency table. There are certain rules that relative frequency follows. The first is that if you add all the frequencies, the answer should be 100% or 1. Sometimes, because of rounding error, we don't get 1, but that's all right. That's okay. There's this thing called a cumulative frequency. A cumulative frequency is as you move from class to class, you just add up the frequencies as you go. So your cumulative frequency is said to be the sum of the frequencies for that class and all previous classes. Again, I'll show that to you in a second, but literally it just means we're adding as we go. We're adding frequencies as we go. All right, so this right here is not a class, but it's just a score. So on this test, I guess the highest score was 8 and the lowest score was 3. And so this saying one student got 3, 8 students scored 14 on this test. Right? Assuming it's out of 8. So a good number of you guys got a perfect score. 8, sorry, I had the wrong button. So cumulative frequency is on the first class is going to be 14. And the next class, the cumulative frequency is going to be the sum of these two. 14 plus 21 is going to be 35. The next one is going to be 14 plus 21 plus 11, which gives us 46. Yes? That's just there. You're accumulating frequency as you go. Now, the next frequency is 6, correct? What's 6 plus 46? And so the next one is going to be 52. What's 52 plus 4? 56 plus 56 plus 1. And so this means 57 people took this test. Does that make sense? Does that make sense? 57 people took this test. Out of those 57, one person's got 3 out of 8. Out of those 57, 14 people got 8 out of 8. Questions there? Questions there? All right. Again, so your cumulative frequencies, you're just adding up the frequencies. One way to see it right here is this cumulative frequency is just going to be 14, while this 35 right here is going to be 21 plus 14, while this 46 right here is going to be 11 plus 21 plus 14. This 52 is going to be all of these added together. Yet as we're going down, we're adding them up. Questions there? All right, so onto your relative frequency. Your relative frequency says take the frequency and divide it by the total. So in other words, in this first one, 14 divided by 57, which rounded to 2 decimal places is 0.25. And then 21 divided by 57, 0.37, and so forth and so on. And that gives me my relative frequencies. Again, the way you read this right here, this is saying 37%. This is saying 37% of students. It's gonna take forever. Give me a second here. Relative frequencies, divide. This right here is saying 37% of students scored 7 on the test. This is saying 21 students got 7. This is saying 37% of the students got 7 on the test. It's the same thing, right? One is just a percentage. Questions there? All right. Filling out the table right here. And remember, there's this statement right here that the your frequencies, your relative frequencies should all add up to 1. Because we were rounding, sometimes when you add them up, you don't get 1. In this example, you got 1.01. But this is just a rounding error. If I added up the fractions instead, I will get 57. I will get 1. I'll get 57 out of 57. This is just a rounding error. It is always going to be 1. Questions there? All right. And then they have the table for us. A histogram is a graphical representation of a frequency distribution for quantitative variables, right? A histogram consists of bars, 1 for each class. The height of each bar represents the frequency or the relative frequency. We've seen histograms before. There's a histogram and then there's a bar graph. When you have qualitative data, the L, qualitative data, you use a bar graph. When you have quantitative data, you use a histogram. Histograms, they touch each other. See how the numbers are right next to each other? Bar graphs, they don't touch each other. That's a small difference between the two. And so here you have it right here. Just like I showed you a little bit earlier, the two graphs look exactly the same. The only thing that has changed is the y-axis values. This is a count. Remember, this was 14. Sorry. Yeah, remember this was 14 right here. And so this right here goes up to 14, while the 14 represents 25%. And so the histogram, the relative frequency histogram goes up to 25%. All right? But it's the same data, the same information. Question there. So if I ask you to draw a histogram, you could create a histogram right now? Yes? So basically you would have to put the classes in down here and then just go to the basically undo. Basically you just have to put the classes down here and then just go to the right height. In this case 14, so this goes up to 14. Any other questions there? All right, cool. Again, just think of this as a way of displaying data. I am saying students who scored between oh, this is a different histogram to this one, isn't it? Because these are 8 cents. So I can't say Houston. People who drive between 1 and 8 miles. This is how many people drive between 1 and 8 miles to get to work. Between 8 and 16, between 9 and 16 miles, this is how many people drive between 9 and 16 miles to get to work, and so forth and so on. All right? All right. So that takes us to the shape of histograms. A histogram gives us a visual representation of the data set. Analyzing and understanding the shape of the histogram can give us an understanding of the data set. Generally, a mound-shaped histogram is said to be symmetric if half of the graph is on the left and half of the graph is on the right, and they mirror each other. This right here is a classic example of a symmetric histogram. Question there. A mound-shaped symmetric histogram. Basically, all they're saying is that there is a center. And then from that center, the data tapers off evenly on each side. Generally, most data sets aren't exactly this way. They're approximately symmetric. Question there. But of course, all data doesn't show up like this. For example, if I were to give you guys a test, this is not what the test grades will look like, right? Right? Because most people will score 100. This is saying basically most people score 50% and then the grades taper off from there, right? That's not all data sets look like this, right? If we're talking about students' height in the classroom, then they would look like this, right? But not all data sets are symmetric. For example, you can have what's called a uniform data set. In a uniform data set, all of them have exactly the same chance of happening, so they have the same height. In real life, what might be a uniform distribution? What might be a uniform distribution in real life? Not the age of tires, not the weight of tires, the height. The number of shoes people have? No, that will not be uniform. Something that the chance of it happening is, oh, there you go. The time of arrival of a bus. Generally speaking, that's uniform. The chance of it arriving on time, late or early is approximately the same. Maybe that might be uniform. Example right here is what's called a skewed data set. If I draw a line down the middle of this data set, this would be the left side and this would be the right side. Yes. When the tail of the data is on the left side, see the tail? The tail of the data on the left side is said to be negatively skewed or skewed to the left. When the tail is on the right side, the plus right here, is said to be positively skewed or skewed to the right. Generally, those are the three I want you to remember: your mound or your symmetric graph, skewed to the left, or skewed to the right. For example, students' test grades are normally skewed to the negatively skewed to the left, because most students would score, 80%, 90%, 70%. Most students, but a few students who might have been sick or who came late to the test, but a few students will perform badly on the test. But most students will do very well. Yes? And you go talk to those students who perform badly, there is some kind of reason why that happened. They were sick that day. They had to work, until 2 o'clock in the morning. There are outside reasons, generally speaking, that affect their performance. But generally, for example, test scores are skewed to the negatively skewed. Questions there? What kind of data is right skewed? Housing data, the house prices are negatively skewed. Most people pay, maybe $100,000 for the house, maybe 200,000 for the house, but a few people, paying maybe 1.1 million. A few houses are just way out there, right? That's positively skewed data. Questions? The longer tail gives you the direction of the skewness, skewed left or skewed right. All right. And so why are we doing modes now? Oh, multimode document. We'll do modes and we'll come back and do modes again in a second. But quite simply right here, if there is one point or one class that is the highest, that is called the mode of the data set. The mode is the thing that happens most often. And so in this example right here, you can see this class right here happens most often. And so that class is called the mode, the peak or the high point. Sometimes a data set can go up and down, up and down. And when you have this right here, we call it a bimodal histogram because there are two distinct peaks in the data set. All right, questions there? All right, and the last thing is an ohive. Hopefully I pronounced it right. An ohive is simply the graph of your cumulative frequency. If you recall, your cumulative frequency is just us adding up the frequencies as we go. If I was to take my data and draw a cumulative frequency graph, it would look like this right here, and then right here, and then right here. Remember histogram? I'm doing a cumulative frequency histogram. If I was to do a cumulative frequency histogram, this is what it will look like. What the kind people did was they said, this is kind of hard to read and kind of hard to see. And so what they did was they put a dot at the center. They put a dot at the center of each. They put a dot at the center of each box. And then they deleted the boxes and they connected them by a straight line. And that leaves us with an ohive. The key thing about the ohive right here is kind of easier to see when the graph is growing and when the growth is starting to slow down. Question there. But the key thing is just a cumulative frequency graph. Using the ohive, you can estimate the total number of days with a high temperature lower than or equal to 40 degrees. So they simply find the 40-degree marker, and then you go up and you go over. That number is 119, 117. And so, oh, there it is, 117. And so what they're saying is that 117 days where the temperature is less than 40 degrees. Questions there? Questions there? Last name? Dixon.
Thank you.
All right, so that's the end of chapter 2.1. We're going to move into 3.1 next. Measures of central tendency. How we doing out there? It's Wednesday. This is supposed to be hump day. This is the day you guys have most energy. You know, when you guys show up on Monday, you guys are all tired because you didn't stayed up all night, all week. You all just had too much fun on the weekend, right? And so you're all tired on Monday. And then on Wednesday, you guys finally got some rest, so you got some energy. And then Friday, you guys are looking forward to the weekend, and so you here because you have to be, right? So this will be my best day. Yeah. I have a theory. Wednesday is the best day of the week for learning. No, I gotta get a lot done today. All right. So measures of central tendency. In statistics, when we say measures of central tendency, what we mean is a calculation that tells us what the middle of the data is. When we say measures of central tendency, we say a calculation that tells us what's the middle of the data set, right? For example, if I told you I scored 90% on my first test, and on my second test, I scored 92. Well, what's in the middle of that data set? 91, correct? Yes. And so that's all we're doing right here is we're finding a way to calculate the center of your data. Now it turns out, well, we teach you three of them. There are actually a lot more different ways, but these are the three ones we focus on. The mode, the median, and the mean. Let's get to them, shall we? The mode of the data set is simply the data set that occurs most often. The mode of a data set is simply the amount that occurs most often. Example, I have a data set right here, 0, 1, 1, 1, 1, 1, 2, 2, 3, 3, 6. Which number occurs most often in this data set right here? So therefore, the mode for this data set is 1. Okay, that's it. The mode for your data set right here is 1. There are some rules for the mode for a data set. If you have two numbers that occur most often, or there's a time, for example, I have 1, 2, 3, 4. If I added in two more threes to this data set, then this data set will have two modes. The modes will be both 1 and 3. Yes? But we never go past more than two modes. If there are like 4 or 5 numbers that are tied, we simply say there is no mode. There is no mode in the data set. All right? Question there about the mode. The advantages of the mode is that it is simple to calculate. Excuse me. The advantages of the mode is that it is simple to calculate. And in certain circumstances, the mode is the only measure of central tendency that you can calculate. For example, if you're looking at fashion, you just look at which purse sold the most, and we can say that's the mode, or that's the average purse, right? But it's not really possible to find an average of purses, yes. And so there are some places where the mode is useful. The disadvantages of the mode is that sometimes the mode does not give you the center of the data. Okay? Sometimes if I added in some more numbers into this data set, for example, if I added in 7 and then 8 and then 9 and then 10 and then 11 and then 12, the mode would still be 1, correct? But 1 is, you can't expect 1 to be the center of this data set, right? I got numbers 12, 11, 10, right? Because it occurs most often does not necessarily mean it'll be at the center of the data set. Questions there? Right? So those are your advantages and your disadvantages of your mode. The second thing we want to calculate or learn how to calculate is the mean of the data set. And your mean of your data set is what's called the arithmetic average. Your arithmetic average is found by adding up all your entries and then dividing by the number of entries. Yes? It's something that a lot of us are very familiar with because we had to do it to calculate our test, our overall score. So if a class had, say, 5 tests, and I wanted to find my average score, you had to add up all 5 numbers and divide by 5. Yeah, that's your mean right here. I think I have an example coming in a second. Let me go to the example first, and then I'll come back to this right here. So During the semester, a student took 5 exams. The population for the exam scores was 78, 83, 92, 16, and 85. Find the mean or find the average. All you have to do is simply add all those numbers up, 78, blah, 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 divide by 5, and that gives us an answer of 81.2. Questions there? This is a measure of central tendency, because if I was to draw a number line, and let's start right here. This is 70, this is 80, this is 90, this is 100. And if I were to put the scores on this number line, the first score is 78, that's right around here. 83, that's right around here. 92, that's right around here. 68, that's right around here. And then 85, which is in the middle right here. The average of 81 right here will sit right in the middle of the data set. The average of 81 will sit in the middle of the data. There's approximately the same number of numbers below as numbers above. Yes? And so that's why it's called the average. It sits in the center of the data. Questions there? All right. Now, when it comes to finding the average, there is a small distinction that we want you to be aware of. There is a small distinction that we want you to be aware of, and that is we want you to be able to tell us when you're calculating a population average and a sample average. You guys remember the difference between population and sample? The population is everybody. The sample is a subgroup, yes? Right? So for example, let's say I wanted to calculate after I give the first test, the average score on the first test, right? Assuming everybody took the test, I could just add up all 25 of you guys' scores and divide it by 25, and that will give me an average. Yes? And so they will call that, right? That number will be called the mean, and this will be called the population mean. Right? Now let's say next semester comes along. I remember how you guys did, and I realized you guys didn't do so well. I said, oh no, I can't have that happen again. And so what happened is I redesigned the test. I made a new test. Hopefully that test, better aligns with the stuff I talked about in class and all that good stuff right here. Yes? But I don't want to give that to the class yet because it may be a harder test. I don't want to be mean to you guys. Yes? And so what I can do is select 10 students from my class and say, hey, count my office hours. I want you to take this test, and then have those 10 students take the test. I can then take the average of that test. That average will be called what's called a sample mean. Not everybody took the test. Only a smaller group of students took that test. All right? Questions there? It turns out whether or not it's a population mean or a sample mean, the process of calculating is exactly the same. Simply add up all the numbers. By the way, mathematically, this is how you say add up numbers. Add up all the numbers and then divide by the number of numbers that you have. And then divide by the number of numbers that you have. It's exactly the same calculation right here. Add up all the numbers and then divide by the number of numbers. Questions? When you have a sample, we use lowercase n. In the example I talked about, n is 10 because I had 10 students come to my class. When you're talking about a population, you use capital N. And in this example, again, capital N is going to be 25 because there are 25 students in the class. All right? But that's just notation because, like we said, it's important to be able to distinguish between the sample and the population. Okay? The population is correct. The sample we know is wrong. So we always have to keep that in mind. That's one of the ways they highlight the fact. Questions there? By the way, do you know how to write the Greek letter mu? It kind of go up and then down again. The Greek letter mu, it's pronounced mu, pronounced mu. It's spelled mu, it's mu. And then this one right here, this is said to be X bar. That's how it's pronounced. It's said X bar. Your average X bar. Questions? All right, cool. We did this example right here. Again, notice the formula right here, mu. That is because I took 5 exams. If, for example, I took 4 of these exams and I calculated an average, then that would have been a X bar, right? If I did this X bar and I did some XI and I only used the first 2 tests, I went 78 plus 83 and I divided by 2, this would be a sample mean. Okay? What's 78 plus 83 divided by 2? The distance is 5. To go from 78 to 83 is 5, right? What's half of 5? What's half of 5? 2.5. So the middle is going to be 2.5 away. So this is going to be 80.5. The correct average is 81.2. Notice that the sample mean is off by a little bit. Yes? This was always true for samples. Whenever you take a sample, you know the number is not going to be right. But generally, it's going to be close, yes? Notice right here, I have X bar right here for this calculation. Questions? All right, cool. All right, the median of a data set. This one's interesting. Anyone knows what the median of a data set is? Middle number, yes, yes. The median of a data set is found by putting all the numbers in order of size and then picking the number in the middle. It is found by putting all the numbers in order of size and choosing the number that's in the middle. So it's a little bit more complicated than you think. If you have an odd number of numbers, you just pick the number in the middle. Right? If you have an odd number of numbers, you pick the number in the middle. But if you have an even number of numbers, there'll be 2 numbers in the middle, yes? If you have an even number of numbers, there will be 2 numbers in the middle. Yes, look right here. There are 2 here and 2 here. So there are 2 numbers in the middle. You take the average of those 2 middle numbers. Did they not write it down? Oh, there it is. You take the average of the 2 numbers to find your median value. Questions there? So, for example, during the semester, again, the same numbers right here. The scores were 78, 83, 92, 60, and 85. If you want to find the median, what you need to do is put that data in orders of size from smallest to largest. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then what you want to do is pick the middle number. Now, let me give you a formula that can help you pick the middle number. If the number is odd, if n is odd, what you do is go n plus 1 divided by 2, and this will give you the position of the number you're looking for. How many numbers do I have right here? 5. And so you go 5 plus 1, that is 6. 6 divided by 2 is? I'm looking for the third number in line. That will be my middle number, right? This helps. Let's say I gave you 51 numbers. Well, which number am I looking for? 51 plus 1 is 52. Half of 52 is 26. You're looking for the 26th number. That's going to be your middle value right there. Questions there? Another example. Eight patients undergo a new surgical procedure. The number of days spent in recovery for each is as follows. Find the median number of days of recovery. We first have to put them in order of from smallest to largest. So we have them right here, 12, 13, 13, 15, 19, 20, 21, 27. They're an even number of numbers, yes? When you have an even number of numbers, you take the total and you divide it by 2, and then you take the next number. So I have 8 numbers in total. 8 divided by 2 is going to be, so that means the 4th number and the 5th number, those are the 2 numbers I'm going to take my average for to find my median. Does that make sense? Does it make sense? All right, so 8 divided by 2 is 4. 1, 2, 3, 4. And the next number in line, 19. I take the average between those two numbers. 15 plus 19 divided by 2 is 17. Yes? Yes? And so the median will be 17. Questions there about finding the position of the median. If it's odd, add 1 and divide by 2. If it's an even number of numbers, divide by 2. The number of numbers you have, divide that by 2, and then take the next number. Right? So if I had 100 numbers, 100 divided by 2 is, so the 50th number and then the 51st number, those are the two numbers I will take the average of. It's always only two numbers when you're doing the median. All right? Questions there? All right. And so take those two middle numbers, take the average, and that gives a score of 17. So that's going to be my median right there. Questions? Okay. That's the end of 3.1. Probably. Oh no, that's not the end of 3.1. Yeah. And 3.1. All right. Before I do this right here, there's something that I need to show you. If you go onto the internet machine and you're typing SALT space and then you type in web design, this will bring up something called, you can see it right here, statistical analysis and learning tool for WebAssign right here. I think I actually have it already saved as one of my little things. But you should go ahead and have it saved as well. It actually works better in Chrome than in the other browsers. But you want to save this page right here, salt. Oh, that's the wrong one. It's the first one. This is what salt looks like. You can see the classic WebAssign colors, your send gauge right here. But what salt does is those numbers that we were looking at right here, salt allows us to calculate those numbers. This is part of the reason why I said you did not need a fancy calculator, because a lot of the calculations we need to do, salt will do them for us. All right? Questions there? All right, so let me see if I can get a data set that I want to use. Let's use airline performance. I hit select right here, and then let's just select I want a number. That's categorical. Next. Let's look at on-time arrivals. So I'm just going to click on on-time arrivals and going to hit select right here. And so these are the number of on-time arrivals that they've had by year. Oh wow, that's interesting right here. And then once I have those on-time arrivals, I can then go into what's called descriptive statistics. See right here, your descriptive statistics. You're gonna click right here, and then your descriptive statistics will do all the calculations that you're looking for. Let me uncheck all of these so you can look at them one at a time. So for example, if you want to find the mean, you just check the mean button, and then it'll give you the average right here. It added up all the numbers and then divided by, I didn't know how many years they had, and gives us the mean right here. Good. If you wanted to find how many numbers, you hit on N right here. That gives you there are 120 years in the data set. Is that possible? 120 months maybe. That's how many were in the data sets. Yes. If you wanted to find the median, it's right here. Click on the median. This right here is going to be your median score. It does not do the mode, however, but I guess that's all right. That's okay. Questions there? It can draw your histograms for you. And this one right here, charts and graphs. You click on your charts and graphs right here. Okay, bar chart, no. No, no problem. Oh, I got to select one first. On timer. There we go. It will draw the histogram for you. I need to put in the bin class width. Remember the calculations for the class width? Take the highest score, subtract the lowest score, and then divide by the number of scores. Let's put the starting point at 30,000. And let's put the bin width at 500. I'm just estimating here. Right here. And is that too big, too small? What is it saying? Cannot display more than 500 bins. Oh, my bad. Let's go with 12. Let's go with 10 bins. That's fine. There we go. Why is it upset? Yeah, I put 100. I put 10. Why is it upset with me? Let's go with 100. Anywho, if I had a simpler data set, it'll be easier for me to figure out. But it will graph them for you as well. You just gotta select the right numbers in there. So data sets huge. Normally our data sets will be much smaller, so that's not going to be much of an issue. We'll get to the distribution calculators and inferential statistics a little bit later on. But the key thing right here is that this will do most of the calculations for you. I will allow you to use it during the test, so you can save the web page, and so you can just click on it to pull it up. Also, several of your homework questions will use salts. There'll be an orange button. You just click on the orange button, and then it will load salts for you. All right? Questions there? All right, so let's get back. All right, so we continue 3.1. I want to double check something first before I. The same thing. Oh, yeah, it's the same. All right, so yeah, I'm right. All right, so we talked about three things right here: the mode, the median, and the mean. Yes, and I kind of talked about the mode as being like the worst of the three. Yes, because the mode does not necessarily give you the center number. If I have a whole bunch of numbers and zero happens to occur 3 times, and that's the mode, that doesn't necessarily mean that's the center data. Yes. The median and the mean tend to be better measures of the center. And let's go ahead and compare the two. The way we talk about comparing the two, the mean and the median, is by use of something called resistance and shape. If the data set has a shape that is symmetric among the shaped symmetric graph, it will turn out that the mean, the median, and the mode would actually all be the same value. If you have a symmetric data set, highest in the middle, and you slowly taper off on both sides, your mean, your median, and your mode will all be the same value. Okay? Questions there? On the other hand, if we are skewed to the right, i.e. we have outliers on the right side, the mean, median, and mode will no longer be the same value. By just looking at this picture right here, can you tell me which one's going to be the mode? Let's go A, B, C. Which one's going to be the mode? The first one, the second one, the third one? The first one is going to be the mode. Which of the other two is going to be the median? B or C? B, and then C has to therefore be the the mean. Okay. The way we say this right here is this: when your data gets skewed to the right, the mean gets shifted to the right. There's another way of saying this right here. We say that the median is resistant. The median moves less than the mean, and so we say that the median is resistance. It did go higher because I have more data on the right, but it did not move as much as the mean did. Does that make sense? The median is resistant to outliers or skewed values. Think about it this way. Let's say I have three numbers, 1, 2, and 3. What's the median for that data set? Gonna be 2, correct? If I added in 1 million to that data set, so 1, 2, 3, and then 1 million, what's the median for that data set gonna be? I'll write it down for you. 1, 2, 3, and then 1 million. What's the median for that data set going to be? 2.5. Yes? The number in the middle right here, the median is going to be 2.5. So even though I put in 1 million, right? The median barely moves, right? The median is resistant. But the mean is going to change by a huge amount, right? When I just had 1, 2, and 3, the mean was 2, correct? But when I add in 1 million, what's 1 million divided by 4? 250,000? When I add in 1 million right here, I mean, there's a lot of zeros. The mean will become approximately 250,000. What's the average of 1, 2, and 3? 6 divided by 4 is 2.5. 250.25. The mean is going to go from 2 all the way to 250,000 by just adding one number into the data set. Yes? And so the mean will move towards the outlier. The median is resistant. It will not move as much. It'll always move, but not nearly as much as the mean. All right? Question there. If we have it flipped backwards, IA skewed to the left, everything will happen, but in reverse. So this value right here is going to be the mode, right? Then this is going to be the median, and then the last one is going to be the mean. Yes? When we skew to the left, the mean gets pulled to the left by a lot. The median will resist. And so because of that right here, the mean will be the smallest of the value. The mean will be less than the median. Questions there? Any questions about resistance? Or about how skewing the data, left skewed or right skewed, affects the mean? If I'm skewed to the right, the mean gets pulled to the right. If I'm skewed to the left, the mean gets pulled to the left. Questions there? Cool. All right. That's what we have for you guys for today. Let me take attendance.